folks, welcome to another set of Chemistry 1 video notes. Today we'll be talking about atomic structure, how the theory of the atom has changed over time, and how we can calculate the average atomic mass. The standards that we'll cover in this lesson are C.2.1 and C.2.2. The phrase atomic theory encompasses the idea of the atom. It's a scientific theory, which means that we can be presented with new data and then revise that theory. Let's look at some of those revisions from the last 2,500 years. Democritus, a Greek philosopher, is credited with coming up with the idea of the atom. He was philosophizing one day about how many times he'd be able to cut something in half until he couldn't cut it in half anymore. And he theorized that there would be a small particle that couldn't be divided anymore, and he called that particle the atom. Many years later, in 1803, John Dalton, a British chemist and physicist, came up with what is known as Dalton's atomic theory. He had four postulates to his atomic theory. 1. All matter is made up of atoms. Atoms are indivisible and indestructible. 2. All atoms of a given element are exactly identical in mass and properties. 3. Compounds are formed by two or more atoms of different kinds, and they're made of specific ratio of those different kinds of atoms. And 4, a chemical reaction is just a rearrangement of the atoms. Years later, in 1989, J.J. Thompson performed an experiment with cathode ray tubes and discovered the electron. He found that when you pass a high voltage through two plates, it would create a stream of light, and that light could be bent when you place it near a negative or positive charge. This led J.J. to the plum pudding model of the atom. Plum pudding was a popular dessert back in the day, but you can just think of chocolate chip cookie dough, where the dough itself is a positive mass, and the chocolate chips are the negatively charged bits inside of the positive mass. Ernest Rutherford came by in 1910 and discovered that Thompson's theory was a little incorrect. Instead of an atom mostly being a large positively charged mass with negative chunks inside of it, Ernest theorized that there was actually a very tiny mass in the center of the atom, which holds all of the positive charge. Outside of that mass, and moving at random, were the electrons in Rutherford's model. He determined this using the gold foil experiment. He shot alpha particles through a piece of gold foil and examined where they landed on the other side. He expected the alpha particles to just bounce off the gold foil and none of them to go through. If J.J. Thompson's theory was correct, then that's what would have happened. Rutherford noticed, though, that most of the alpha particles actually went straight through the gold foil, but some of them actually did bounce off, like he expected. This led him to believe that there was a lot of empty space in an atom, and in fact, the positive charges, which still have to exist because they deflected the alpha particles, were just really small, and that's where he came up with the idea of the nucleus. In 1913, Niels Bohr came along and added to the atomic theory, stating that those electrons are not actually moving at random. They're moving in very specific circular orbits around the nucleus, each orbit with a different amount of energy. He also theorized that moving from one orbit to another would either cause the electron to release or absorb energy. 13 years later, in 1926, Erwin Schrodinger came up with yet another model. With his equation, now known as the Schrodinger equation, he predicted that electrons don't actually move in circular paths. They do move at random. However, there are very specific areas of probability in which they're most likely to be. These areas of probability make up different shapes that we call orbitals. We'll learn more about those later, but each orbital then has a different amount of energy, much like in Bohr's model. Finally, in 1931, James Chadwick came along and discovered the neutron. He came up with the idea of the neutron in order to explain away why isotopes of uranium could decrease in mass, but still be atoms of uranium. This told us that neutrons had a mass because they could go away and the uranium atoms would lose mass, but they didn't have a charge because they still just stayed uranium atoms. So now that we know what all it took to get behind our current theory of the atomic model, let's study it a little bit more. There are three particles that are smaller than an atom. These are known as subatomic particles. There are protons, neutrons, and electrons. Protons exist inside of the nucleus, are positively charged, and weigh 1 atomic mass unit, or AMU. Neutrons are very much like protons. They exist inside the nucleus and they weigh 1 AMU, but they do not have a charge. They are neutral. And finally, electrons exist outside of the nucleus. They're negatively charged and they basically weigh nothing. Their mass is so small, we just say that it's 0 atomic mass units. When we're looking for an atomic number, all we have to do is find out how many protons are in the atom. If there are 6 protons, the atomic number is 6. 7 protons, the atomic number is 7, and so on and so forth. Since protons and neutrons are the 2 subatomic particles that have mass, we use those to find the mass number. Each proton and neutron weigh 1 AMU, so we just add up the protons and the neutrons to get the mass. And our charge is the number of protons minus the number of electrons. Since protons are positive and electrons are negative, we have to subtract the electrons from the protons to determine the overall charge. In an atom, the number of protons always equals the number of electrons. So there will never be an atom that has a charge. Sometimes it gets a little confusing when we have all of these terms that mean something very similar. So I would pay very close attention to the following definitions for some of those similar words, and make sure you learn the differences. An element is an identification. All particles of a particular element have exactly the same number of protons, and any atom that has the same number of protons as another atom would be identified by the same name. For example, the element carbon, no matter whether you have atoms, ions, isotopes, etc., any particle of carbon will have exactly 6 protons. An atom is the smallest particle of an element. It has protons, neutrons, and electrons. The special thing about an atom is that it always has the same number of electrons as it does protons. That's what makes it an atom. Having an equal number of protons and electrons means that atoms do not have an overall charge. Ions, on the other hand, are just like atoms, except the number of electrons will be different than the number of protons. Some ions of an element might have more electrons than it does protons, making it negative, or it could have less electrons than protons, making it positive. Finally, isotopes are atoms of an element that have a different number of neutrons. In other words, a carbon atom might have 6, 7, or 8 neutrons, but it's still carbon. We name isotopes based on their mass numbers. So if a carbon has 6 protons, a carbon with 6 neutrons would be called carbon-12, because 6 plus 6 is 12. If it had 7 neutrons plus the 6 protons gives us 13, so we call it carbon-13. Our last bit for today is learning how to calculate the average atomic mass of an element. The average atomic mass is what's reported on the periodic table. It isn't a mass number because it usually comes in the form of a decimal. This is the average of all of the mass numbers of all of the isotopes that naturally exist for that element, based on those isotopes' natural abundance numbers. The natural abundance is represented as a percent and tells us how many of all of the naturally occurring atoms of that element are this isotope. In other words, if I had 10 carbon atoms and 6 of them were carbon-12s, 4 of them were carbon-13s, you'd say the natural abundance of carbon-12 is 60%. The average atomic mass is found by multiplying each of the isotopes' mass numbers by their natural abundances and then adding it all up. All right, let's do a real quick example of how to find the average atomic mass. Our example problem says that we have 3 different isotopes of magnesium that naturally occur in nature. We have magnesium-24, magnesium-25, and magnesium-26. It also says that our natural abundance for magnesium-24 is 78.7%. Our natural abundance for magnesium-25 is 10.13%, and our natural abundance for magnesium-26 is 11.17%. The 24, 25, and 26 are our mass numbers, and these percents are our natural abundance. This is a little bit easier when you make these percents actual decimal numbers instead of with the percent sign. All you have to do is move the decimal place over 2 places. Now there's only 2 steps left. You have to multiply the mass number by the decimal percent for each isotope. Once you've done all that, you get 24 times 0.7870 is 18.888. 25 times 0.1013 is 2.5325. And 26 times 0.1117 is 2.9042. You just have to add them all up. And when you add all of that up, you get 24.32 AMU. This then would be the average atomic mass of magnesium.